Welcome everybody, and let me start by thanking the organizers for the invitation. It's a real pleasure to be here. And I also want to tell you that, unlike most of you, I'm actually a physicist. So my presentation will be more in the physics style, but I hope the main ideas will be clear. And if something is not clear, please do not hesitate to ask me to clarify, okay? So I'm going to talk about dynamically emergent correlations, and also I should say that, as in customary in physics talks, I'll acknowledge my collaborators at the very end of my talk. All right, so this is the subject of my talk, and here is the sort of outline. So I'll first tell you what is the dynamically emergent correlation. So roughly speaking, these are just independent particles like Brownian particles, but they are coupled to some fluctuating environment. So it's somewhat similar in spirit to Daniel's talk, last talk. And so this environment is fluctuating. I'll give you very precise models for that. And so that's the general setting. And the whole point about dynamically emergent correlation is that because they share the same stochastic environment, that actually induces correlations between them dynamically. And it is these correlations that we want to focus on. Okay, so I'll talk about a very simple model of switching. Oops, I don't know what happened. How do you get? Do you know how to? Okay, sorry, thank you. Yeah, so it's a very simple model of switching confining potential, which could be a box or a harmonic trap. And what I'm after is to find out the joint distribution of these particles in a non-equilibrium stationary state, and I'll explain to you what I mean by that. And there will be a particular mathematical structure which will come out, which we call the conditionally independent and identically distributed, or CIAD structure. And I know you may not be interested, but there are some recent experiments using optical tweezers. I'll just briefly mention that, which can actually verify much of these analytical predictions of this theory. And then I'll talk very briefly, if I have time, to generalization to other models with the stochastically driven environment, and then I'll conclude. All right, so let's see. So what is the, So what's the general physical setting? So the physical setting is the following. So imagine that you have a bunch of particles, say just a Brownian gas of particles, like this shown by the blue, this thing. And they're coupled to some environment, which is shown schematically here by this red border. Okay, and I'll be more precise later. And this environment is stochastic, and that's very important. It's not deterministic, it's stochastic, and the motion of the environment is independent of particle motions. Okay, so the particles are non-interacting, they don't interact with each other, but they do interact with the environment, and they do not affect the motion of the environment. Okay, so that's the general setting. And as I said, the stochastic dynamics of the shared environment, so that will induce strong correlations between the particles. So that's the sort of bottom line of my talk. And this is what we call the dynamically emergent correlations. Okay, and we want to characterize how these correlations develop and how they affect the stationary state and so on. Okay, so this idea actually sort of a somewhat similar idea. It goes back a long time back. Oops. Christian Huygens, who was a Dutch mathematician in the 17th century, but he was also a very expert clockmaker. Okay, and so once he was a bit sick at his home and he was doing some experiment. So what he did is he took two chairs like this, and he put a wooden beam across the two chairs, and then he hung two pendulums from it. Okay, so the pendulums are basically non-interacting, and then he just pushes one of the pendulums here, the left one, let's say. So in the beginning, they don't talk to each other. But then with time, after some time, he saw that, they are actually get completely synchronized, correlated, and they, move in sort of synchronized way, okay? So, but of course, this system is slightly different from what I'm talking about. So here, what happens is that this pendulum on the left, when you push it, it actually moves the wooden beam. So that's the environment here. So it actually affects the motion of the environment, which in turn affects the other pendulum, and then slowly they get synchronized, okay? So in our system is fundamentally different from us. In our system, the particles, which are like these pendulums, they do not affect the motion of the environment, okay? So in that sense, it's different, but the the idea that they get correlated is sort of similar somehow. Okay. So here is the sort of very simple model that I have in mind, and we will keep focusing on this model. So imagine that you have a box of linear size L1, and you have some Brownian particles with reflecting boundary conditions at the wall. So these particles just move around, totally non-interacting, independent Brownian motions. And but at the same time, the box itself is fluctuating between two values, L1 and L2. Okay? With rate R1, it goes from L1 to L2, and with rate R2, it comes back from L2 to L1. By rate, I mean it's a continuous time dynamics. So basically, you are at L1, you wait for an exponentially distributed time with parameter R1, and then you change to L2, and then you stay at L2 up to an exponentially distributed time R2, and then you come back to L1. So this is stochastically fluctuating the box size. And if a particle happens to be here between the two boxes L1 and L2, some of this, okay, so, okay. Yeah, if it is between here, when you push this box, particles just gets translated to the wall, just gets pushed by the wall. Okay, so that's a simple situation. And so more precisely, so what the box size is doing, L of t is doing a sort of dichotomous motion here, telegraphic process. So it stays at L1, as I said, up to an exponentially distributed random time and with parameter R1, and then it switches to L2. Then it stays at L2 up to an exponentially distributed time with parameter R2, and so on. Okay? And so this is the box is doing, and the particles are just moving independently with reflecting boundary conditions. So that's the model. And the goal is to ask, what is the joint distribution of the particle positions? You can think of in any dimension of these, n particles here, and what is the joint distribution at time t? And in particular, I'm interested in the stationary state when the time goes to infinity, if there is a stationary state. Okay, so that's the problem. Okay, and all right, so before asking this general problem, it turns out to be very hard to solve. But we'll first consider a particular limiting case when L1 is 0 and L2 is infinity, and R1 is infinity and R2 is R, which means basically you have this gas of particles, and think of in one dimension for simplicity. You have this gas of particles, so you squeeze them instantaneously. So that's why R1 is infinity, and immediately release them and let them diffuse freely. And again, after some random exponential time, you just squeeze them back to the origin and you release them, and so on. Okay? So that's a particular limiting case. So which means basically, if you are thinking of just one dimension, just as for simplicity, so if you look at these space-time trajectories, so you have n Brownian motions which are independent. So each of them is just moving Brownian up to exponentially distributed time. So this is the free diffusion. L1 here is infinity. Sorry, L2 is infinity. And after that, you instantaneously squeeze them to the origin. So you reset them back to the origin and instantly release them. Again, they move, free diffusion up to an exponential time tau 2, and so on. Okay? And so R is the only parameter here. And we want to know what is the joint distribution of the particle positions at time t. Okay? So this, a special case of this, which is the n equal to 1 for a single particle. So this was actually studied long time back by Martin Evans and myself. So this is called, basically it was a basic model of what is called the stochastic resetting. I'll just remind you of this n equal to 1 case, and then we'll see how to generalize this to finite end. Okay, so if you have one single particle, and if you have n particles, it's like moving in n dimensions, if you like. Okay, so single particle. Let's focus on the single particle case. So single particle means basically you just have a single Brownian motion, let's say in one dimension for simplicity. And again, it diffuses freely up to an exponentially distributed random time, and then it just gets reset, it gets squeezed to the origin, and then again instantaneously, it starts moving up to an exponential distributed time, and so on. Okay, so that's the model. So if you are doing, so this is a model which is in continuous time. So if you are updating your dynamics, if you are doing simulations, so it's very simple. So you just update the position x at time t plus delta t. is, maybe I'll use a pointer which is, there's no stick here, okay. So, so this is, so with probability R, because R is the rate, so with R delta t, this is the probability in a small time interval delta t. With this probability, it goes back to 0. And with the complementary probability 1 minus R dt, it just does diffusion. That means you add a noise, which is just a white noise, with diffusion constant d. So this is just a dBt, if you like. So that's it. So this is the model. You know, R is the only parameter. It's a very, very simple model. Okay. So how do you solve this model? So we want to know what is the PDF of the position, PR of xt. The subscript R means with resetting. And it starts from initial condition, which is the Dirac delta at x equal to 0. And we want to know what is PR of xt. Okay? So when there is no resetting, when R is 0, then we all know that this is just a plain simple Gaussian diffusion. So P0 of xt is this. And now I switch on this resetting and I ask what is PR of xt. Okay? So this is actually a very simple problem to solve. So let's see how to solve this. So essentially, you exploit a renewal structure of the problem. So what is the renewal structure? So I look at up to time t of my trajectory. Okay? So there are two possibilities, that within this time t, either there is no resetting, which happens because it's a Poissonian resetting, so it happens with probability to the power minus RT. And in that case, you just have a free propagation. So then it will be just P0 of xt. So that's the first term. And the second term corresponds to the case when there are one or more resettings. So in that case, what you have to do is to actually keep track of only the last resetting before t. Okay, so suppose that last resetting occurred before t, tau time step before t, because you don't care what happened before that, because last resetting conditions the particle to be at the origin. So condition on tau, you have just a free propagation, P0 of x tau, which is just a bare Gaussian propagation. And then you have to multiply with the conditional probability of tau. And last resetting, the probability that there is no resetting in this interval is e to the power minus r tau, followed by a resetting events between tau and tau plus d tau, which occurs with probability r d tau. And then you have to integrate the tau from 0 to t. Okay? So that's it. You can check that this is an exact solution. It satisfies the Fokker-Planck equation and so on. So it's a very simple renewal interpretation of this. Okay? And in particular, what you see is that when you take the limit t goes to infinity, the first term drops out. And this integral is very easy to do. And you find a stationary state independent of time, which has a double exponential structure. It's a non-Gaussian distribution. And with a length scale, which is just, you can't see it, is square root of d over r, which is the typical length scale over which a particle diffuses between two successive resettings. Okay? So that's the first thing. So it's a very simple model, and yet it has a very nice, simple stationary state. Okay? And this stationary state, as I said, it's non-Gaussian. It has a cusp at x equal to 0, so mod x. And it's a non-equilibrium stationary state because, why non-equilibrium? Because, because of the resetting, it violates the detail balance because you are resetting back to the origin, but there's no reverse move. So there is always a probability current in the configuration space, even in the long time limit. So therefore, such stationary states with a non-zero current, they are usually called the non-equilibrium stationary state, or NES. So even though it looks like a equilibrium state with an effective potential which is mod x, it's not an equilibrium state. Sorry. Okay, so this was our prediction a few years back, and then very recently, this was actually verified in the experiments of from the Tel Aviv group of Yael Roikman using holographic optical 2Zs, and you see that it works very well, the analytical prediction. Okay, so this is just with a single particle. All right, so now let's look at what happens to when there are many independent particles. Okay. So if you have now n Brownian motions which are independent of each other, and they are simultaneously reset with rate r to the origin. This is remember this is the limit of the box problem when I'm squeezing the box, so they all get simultaneously reset back to the origin with rate r. So I want to know what is the joint distribution of the particle positions at time t. Okay? So again, I can use the same renewal picture. So imagine that between 0 to time t, you have no resetting, which occurs with probability to the power minus r tau, rt. And then in that case, it's a free propagation. So you have just a product of the Gaussians because they are independent particles. Okay? And then you can have one or more resettings. And in that case, again, you have to condition on the last resetting. So once you condition on the last resetting time, you have the free propagation, and then you have to average over the last resetting time. And this gives the exact solution of the joint distribution. It's a very, very simple structure. Okay? But what is interesting here is that first thing you notice that in this stationary state, at any time t, in fact, the joint distribution obviously does not factorize, which means somehow these particles get correlated. Okay? So this is the correlated resetting gas. And these correlations, they are not interactions which are built in. So these are actually correlations which are generated dynamically because of the simultaneous resetting. It's like, imagine in this room, we all carry an independent bell, and so we don't know each other. We just, roam around, and when the bell rings, we all have to come back to the seminar room. And this makes us correlated, basically. Okay? And so this is what we call DEC, okay, dynamically emergent correlations. Okay? And we'll be more precise about that. So how to extract the correlation function? So naively, typically, what you do, you just calculate the 2-point function, xi, xj, and then average, subtract the connected part. But this guy here, because of the structure, you see these are all, okay, I don't have this, somehow this is not working. So P0 of xi is Gaussian, so therefore you see that, if you take the xi for I not equal to j, by symmetry, this is 0, basically. So to detect the correlation, you have to go a little bit higher order correlations. The simplest higher order correlations is sorry, yeah, question?
Maybe, sorry, yeah.
Okay.
I was confused.
All right. So the simplest, higher order correlation is this guy, xi square, xd square, and you subtract off the connected part. And you can actually very easily compute that because, it's just, Gaussian, inside the integral is Gaussian, so you just have to calculate this object. And it turns out that this is a very simple computation, and what you find is that, it's just a scaling function of r times t, and this function is given explicitly by this. So if you plot it as a function of z, which is just the, rescaled time, the dimensionless time, if you like. So this is, you can think of this as time axis. So as time grows, you see this correlation grows as zq for small z, and then it saturates to 1 in the long time limit. So in long time limit, it goes to a constant 4d square over r square. Okay? So this is the correlation which is being generated by simultaneous resetting. Okay? And in the long time limit, the first term drops out, and then again you have this integral here from 0 to infinity, and you just have a very, very simple structure of the stationary state. Okay? And it generates attractive all-to-all interactions effectively between the particles, even though the particles are, to start with, they are non-interacting. And plus, other fact is that they are strongly correlated in the sense that everybody interacts with everybody. It's not just a nearest neighbor interaction. Okay, so it's a very, very strongly correlated gas of resetting particles which are being generated here. Okay? So this is the stationary state. So this stationary state, so even though it's a strongly correlated stationary state, nice thing is that, for such strongly correlated state, usually, to calculate physical observables becomes usually very hard, okay? I'll give you an example of that. But here, you notice that it has a particularly nice mathematical structure which makes it solvable. And this structure is the following. So you see that essentially the joint distribution has a structure. So there's a variable u here, which is in this case the last resetting time, and you condition on u. Once you condition, then they become independent, okay? And then finally you have to average over the distribution of this random variable u, which is h of u in general. And here in this case, h of u is just r e to the power minus r tau, and u is just tau. Okay? So because of this conditionally, this CIID structure, you will see in a minute that you can actually calculate many observables explicitly, and they have quite non-trivial behaviors, okay? So how do we make the calculation? So calculation is basically goes in 2 steps, as I said. So despite the presence of strong correlations, because of the structure you can calculate. So basically all you have to do is to first condition on tau and compute. So then these just IID variables, and for IID variables, you can calculate many observables exactly, and then all you have to do is to average over this conditioning variable tau. So what are the observables? So in physics, typically, I mean, you have a strongly correlated gas. So first thing that, first observable, basic observable is that this is an inhomogeneous gas, okay? So you want to know what is the overall global density, okay, of the particles. So that's the first object. Then you can actually order these particles here, from right to left, 1, 2, 3, etc. You order them and you ask for the distribution of the kth maximum. For example, I can ask what's the distribution of the rightmost particle, so that's the maximum, then second maximum, third maximum, etc. I can ask for the distribution of spacing or gap between the particles, okay? Or I can ask full counting statistics, which means I take an interval minus L2 plus L, and I just count how many particles are there. So that's a random variable, and I want to know what is the distribution of this random variable. So these observables are, sort of motivated, if you like, or motivation comes from random matrix theory, because in random matrix theory, as you know, if you look at the eigenvalues of a Gaussian random matrix like GUE or GOE, so what you see is that the eigenvalues are on a line. They are real eigenvalues. And these are the typical observables that people compute. So for example, I mean, if you look at the average density, then in the large n limit, it goes to Wigner's semicircular law there. And distribution of the first maximum is the famous Tracy-Widom distribution. Then you have this gap distribution, which is called the Wigner-Dyson distribution, full counting statistics, and so on. So here also we have a correlated gas, but very different from the eigenvalue statistics. And we want to calculate exactly the same observables that people do in random matrix theory. Okay? So I'll just, I told you how to compute them, so I'll just flash the results now. So, basically, as I said, you do it for IID variables and then just have to average over this. Okay? So it's very, very simple actually. Okay? So here are some explicit results. So I'll go fast. I mean, you don't have to follow the details, but you get roughly the idea. So the average density. So average density is very simple because you have this joint distribution. So average density, which is just a fraction of fraction of particles between x and x plus dx, average fraction. And this is just the, just the marginal distribution of one of the variables because these are exchangeable distributions. So you just have to integrate over all the other guys except for one guy. And immediately you see that when you integrate all the Gaussians, so only one Gaussian is left. So it's just like the one particle density. And so it's just this same double exponential that I showed you for n equal to 1 case. So this average density does not depend on n, unlike in the random matrix theory where, you get Wigner's semicircular law only in the large n limit. Okay? All right, so this is the average density, first thing. So this is your gas. This is your average density profile of the gas. So that means, the more particles near the center where you are resetting, near the origin, and then they get sparser and sparser as you go away from the center. Okay? So then the next is the order statistics. So you can set, mk is the kth maximum from the right, counted from the right. So m1 is the first maximum, m2 is the second maximum, and so on. And so I set k equal to alpha n, where alpha is like an index which tells you, so if alpha is order 1, that means k is of order n, and you are going from right to left, so you are probing inside the bulk of this gas. And if alpha is of order 1 over n, then you are probing near the edge of this gas. Okay? And for simplicity, I just set alpha less than half. For alpha bigger than half, you have to come from the other side, so it's perfectly symmetric. Okay. So what are the results? So the result is actually very, very simple and nice. So first thing is that you find that both in the bulk and the edge, the probability that the kth maximum takes the value w for a given n in the limit of large n, so it actually scales like this. Okay, so in the bulk, so this is some function of w over lambda alpha. So lambda alpha is of order 1. So this is the typical scale of mk, and near the edge, the maximum actually scales like square root of log n, and this is the ln. Okay, but what is nice is that this function f, it does not depend whether you are probing the bulk or at the edge. Okay, it's the same function. And this function is very, very simple. It's actually 2z e to the power minus z squared. With, this theta z means z is positive. Okay. So this is universal. It does not depend on whether you are probing the bulk or the edge. This is very different from random matrix theory, because random matrix theory, at the edge you have a Tracy-Widom distribution, but when you go in the bulk, it's very different distributions. Okay, so this is simple, and then you can check this result, against a numerical simulation, and you see that it works very well, and this completely universal function for the order statistics. Okay, so you can ask for the gap statistics. Gap means the spacing. So again, inside the bulk, if you are probing in the bulk, there of course the typical separation is 1 over n, whereas here, the particles are sparser, so it actually goes like 1 over square root of log n. And again, if you compute the distribution of the gap, I'm not showing you the details of the computations, but again, they are described by the same universal function. Only thing that differs is the scale. The scale in the bulk, it's order 1 over n, and near the edge, it's 1 over square root of log n. And the scaling function is also very simple. I mean, it has a sort of this particular form here. And so if you look at the asymptotics, so it goes to a constant as z goes to 0, and it decays as stretched exponential e to the power minus z to the power 2/3 when z goes to infinity. The fact that it goes to a constant, unlike in the random matrix theory, because there it goes to 0, because in random matrix theory, eigenvalues repel each other. So the probability of two eigenvalues, the gap going to 0, is 0 actually. But here, because the particles attract each other, so it actually goes to a non-zero constant over here. Okay? And so it has a non-trivial, simple yet non-trivial, scaling function. And you can see that, numerically it also works very well. Similarly, you can calculate the full counting statistics. So full counting statistics means I just look at the number of particles between minus L to plus L around a box around this, and I ask how many particles are there. Okay, so say this is a random variable. Given the joint distribution of particle positions, I want to compute this. And once again, I'm not showing you the computation. The calculation is sort of straightforward. So it's again a scaling function of NL over N. So I call it kappa. This is the fraction of particles inside the box, which lies between 0 and 1. And the scaling function is highly non-trivial actually. So there's a parameter gamma here, which is just the RL square. So this is the ratio of the two timescales, diffusive timescales and the resetting timescales. And this function u of kappa is just the inverse of the error function. So this function, if you plot, it is very strange. So this is kappa is varying between 0 and 1. And you see that it sort of starts very small, and then it has a peak, comes back, and then it goes up again when kappa goes to 1. Okay? So these are the asymptotic behaviors in the two limiting cases. And the fact that it sort of goes up, that means the probability that kappa is 1, that means all the particles are near the center, is pretty high because of the attraction between the particles. Okay, so this is all sort of, you can work out everything nicely. And then you see that this structure here, this CIAD structure, this is actually very general. I mean, I talked about diffusive particles, but you can take any sort of dynamics if you like. So, for instance, you can take Levy flights, you can take ballistic motion. All you have to know is the propagator without the resetting, and then it's just a Laplace transform of that, basically. Okay? So you can actually, generate a whole class of solvable correlated gases in their stationary state. So this is a kind of new application of the stochastic resetting. Okay. Very good. So let me just summarize so far. So I started out with this box problem, and I looked at the particular limiting case when L1 is 0, you squeeze it to the origin, and then you release it. Squeeze it, release it, squeeze it, release it, like that. Okay. And then it already has a sort of non-trivial properties for the stationary state, and it's exactly solvable with a strongly correlated non-equilibrium stationary state, which has this CIAD structure. And so question is, how generic is the CIAD structure? If I want to go beyond this limiting case, what can we do? Okay. So it turns out that for general L1, L2, and R1, R2, this is a very hard problem. You still haven't made full progress in this problem. But I want to tell you about a problem which is slightly different, which can be thought of as similar in spirit as this problem, okay? Which turns out to be exactly solvable, okay? So this is the switching harmonic trap, and this is more closer to experiments, as we will see later. And so this is, as I said, is a cousin of this box problem, okay? So what is this problem here? So the problem is, again, exactly similar in spirit. So you have this bunch of n, particles here. A bunch of n independent particles, and they are now in a harmonic oscillator. So it's like an Ornstein-Uhlenbeck process, if you like, except that the stiffness, so potential is mu x square by 2, and the stiffness value, mu, changes between mu1 to mu2, again in the same dichotomous way. Okay? So the problem is very simple. So you have a bunch of Ornstein-Uhlenbeck processes, okay, here. Okay, and this stiffness mu t, which is the strength, and this is sort of similar in spirit in the box problem, because 1 over square root of mu is like the typical extent of the length inside the, so it's a confining potential. So instead of a sharp potential like box, you just have a soft potential, which is the harmonic well. Okay, and mu t again changes from this between these two values. Okay, and I want to know what is the joint distribution of the particle positions in the stationary state. Okay, so that's the problem. Okay, so this problem, it doesn't have a renewal structure. I mean, not manifest at least. So how do you solve this problem? So for this problem, you have to solve a little bit more these things, which is and of course here also in the limiting case, when mu1 goes to mu infinity, mu2 goes to 0, and r1 goes to infinity, r2 equal to r. So this is again goes back to our original problem. So this is a generalization of the original problem, the special case. So how do you solve this problem? So what you have to do is to actually solve by Fokker-Planck way, which means that you have to define the generators. So let me define first P and P of xt, joint distribution of the particle positions at time t, and that the state of the potential is either 1 or 2. So this is the object, so P1 and P2, and there's a coupled differential equation between P1 and P2. And this differential equation, okay, I'll just write it, but it's very simple actually. So essentially, so if the system is in P1, then you have this is the diffusion term, this is the drift term, usual, and then with rate R1 you are going away from P1 to P2, and with rate R2 you are coming back from P2 to P1. So this is just the master equation for that, and similar thing for P2. Okay. And you have to start from the initial condition, which I'll assume that initially, it can be either mu1 or mu2 with equal probability, and all the particles are at the origin. Okay? So this linear equation, it turns out that you can actually solve it exactly in the Fourier space. I'll not go into the details of the solution, but if you define the Fourier transform here, and then it turns out that the n particle problem, if you define k square, which is, there's this kind of spherical symmetry in this problem, k1 square, these are the Fourier modes of each particle positions. Then the stationary state is, you can write down explicitly in terms of this Kumar function, okay, which is a simple hypergeometric function, and these are just the renormalized rates. Okay. So if I give you this formula here, I mean, it's not obvious at all that there is an underlying CIID structure. Conditionally independent identically distributed. Because if I give you this, unless I can invert this Fourier transform exactly, it's very difficult to do any computation, okay, to calculate the correlation function and so on. But it turns out that, okay, this is just a little bit of technical details, but it turns out that this M function has a beautiful integral representation, and which is when you realize it's useful to have books like Gradstein or Abramovich-Stegan and so on. So it has this very nice integral representation, and once you have this integral representation, you can invert the Fourier transform, because this is just a Gaussian inside the integral. Okay, and so when you do that, you actually again recover this CIID structure. So the joint distribution is like individual Gaussians with variance Vu, and this Vu has this form, which is d over u by mu2 plus 1 minus u by mu1. And this random variable u goes from 0 to 1, and it has an explicit distribution, which is given by this formula here. Okay. With a is some normalization constant. Okay. And so roughly speaking, physically, I mean, so many of these problems, the joint distribution may have a, in this problem it was not manifest. Thanks to this integral representation, we could identify this random variable u. But the main problem is to often identify the random variable u. And here, you see that it has this physical interpretation. So d over mu2 is like the variance if it was completely in the state 2. And so u is like the time, fraction of time it spends in potential 2. And 1 minus u is the complementary fraction that it spends in potential 1. And this U itself has a very non-trivial gamma distribution with an exponent which depends continuously on these rates R1 and R2. Okay. So this is highly non-trivial, and it was not at all obvious that when we started this problem that it will have this kind of CIID structure. And once you have this CIID structure, then of course, as I said, calculating any observables in the NES, you can do it explicitly, and it has quite rich and interesting behaviors. So let me focus on one particular observable, which is the maximum. That means the rightmost particle position. So it turns out in this problem as well, again it has a scaling form like this, but the scaling function f here. So the square root of log n is the typical scale of the maximum, and inside the well, and the scaling function, the distribution of the rightmost particle. So it has a very non-trivial, it has a finite support over square root of R1 to square root of R2. And it can either vanish on both support edges, or it can diverge, or it can vanish on one side and diverge on the other side, depending on these parameters R1 and R2. They are just original rates over stiffness. So this is a new extreme value distribution in a strongly correlated random system, random variables, with a finite support. I have not seen any example of an extreme value distribution which is supported over a finite support. I mean, if you look at Tracy-Widom distribution, it has an infinite support also. So this is very nice. So we could calculate this explicitly. And so here is some simulations. You can see that it can, depending on R1 and R2, depending on R1 and R2, it can either vanish on both sides, or it can diverge on one side, vanish on the other side, or it can diverge on both sides. Okay? And again, it's universal in the sense that it does not depend on whether you are probing in the bulk or at the edge. Okay? And also it's a super universal in the sense we can do the calculation for higher D, and it turns out that it's completely independent of D. So it's a really universal distribution. And so, once we discussed this, then we discussed with our colleague Sergio Siliberto, who is an experimentalist at ENS Lyon. And so he has this setup of optical tweezers. So this is for fun. I just wanted to show you. So he has this. So basically, these are colloidal particles, beads inside a liquid like water, and he can create these laser traps. Okay. So these are the 4 different traps. So each trap can contain at most one particle. Okay, because for technical reasons, they cannot put many particles in the same trap. But he puts one particle in each trap, and the traps are oscillating, whatever, going between 2 values in a synchronized way. So that's effectively mimics the original problem. But why did we want to do this experiment? Because he wanted to see, because in real systems, it's in a water, in a fluid. So there is always a hydrodynamic interaction between these particles. In the theory, we are assuming these are non-interacting particles. And so the one interest was to see how the hydrodynamic interactions affect these correlations. Okay. And because they are neglected in the theoretical model. And so he did this experiment, and then he just compared. So for example, if you look at this correlation function, this C2 function that I mentioned, you normalize it with the variance, like this, just this object here. So this is the solid curves are the theoretical formula here. And these are the experimental results. Okay, so this was very surprising because we thought that the hydrodynamic interaction is very important and they should matter, but it turns out that no. The dynamically emergent correlation is so strong that it somehow overwhelms the hydrodynamic interaction which is present in the system. Okay, so therefore it's a real effect. And then he looked at the distribution of M1, which is this guy here. And you see that for different number of particles and different rates of the parameters. And the theory and experiment, they actually match very well everywhere. Okay? So he could do experiments up to n equal to 8 particles. So the main summary here is that the emergent correlations, they dominate over the hydrodynamic interactions. Okay? So hydrodynamic interactions are there. You cannot get rid of them. But these dynamical correlations are so strong that they completely subsume the hydrodynamic interactions. Okay, so then there are other models with CIID structure. So there are many. I will not go into the details, and just to mention, you can think of this general scenario in many situations. So for example, you can take n non-interacting particles in a harmonic trap, but instead of changing the stiffness, you just change the center, okay? Stochastically modulate the center. And then again, they get strongly correlated. Or you can take, the common diffusing diffusivity. You can take n interacting Brownian motion with a non-Poissonian resetting. And finally, there's one model we started recently with Denis Boyer, which is this guy here. Oops, sorry. So this is the resetting with memory. So in these problems, what happens is that, if you take a random walk, normally you are resetting always back to the origin, but so there is no memory effect. But you can actually study a model where you reset not to the initial position, but you have to keep track of the trajectory, of the whole memory of the trajectory, and you choose a time from the past at random, and wherever you were at that time, you reset to that position. Okay, so it has to remember the trajectory. And even in that case, when you take n non-interacting particles, there is again the CIID structure and with memory. So this is a very common. And then going beyond classical models, it turns out that in quantum models also, if you do quantum resetting, for example, you can take bosons in a trap and then you modulate the trap, and that introduces correlations between non-interacting bosons. And so there have been a lot of work which is being currently done. So the main point, to summarize the main point, the non-equilibrium stationary state in all these models, both classical and quantum, so they have this CIID structure. Okay. So one general mathematical question that arises, if you give me a joint distribution, what is the necessary and sufficient condition that it has a CIID structure? Okay. So in the limit when n goes to infinity, so then there's a de Finiti's theorem which tells you that if the joint distribution is exchangeable, then it will definitely have a CIID structure. But for finite n, I do not know of any theorem, and that's a very interesting, challenging mathematical problem. Okay, so let me just summarize and conclude. So the main point I wanted to say is that, that basically, you can have a bunch of particles with no interactions between them, but if they are coupled to a dynamically fluctuating environment, fluctuation is very important, then that induces very strong correlations between these particles, okay? So this is what we call the dynamically emergent correlations. And I showed you some examples, at least 2 examples of switching harmonic trap and box problem. And nice thing about these problems is that they are solvable for many physical observables explicitly, because they have this CIID structure which allows us. Normally, if you have a strongly correlated system, we know from random matrix theory, it took 100 years to solve many of these physical observables. But here, this is a very nice example because it has a particularly nice structure which lets you solve these problems. And moreover, as we see in real systems on colloidal particles in experiments, somehow these dynamically emergent correlations are very strong, so there were other interactions, like hydrodynamic interactions, and they are sort of easily generalizable to many particles like ballistic particles, Levy flights, and so on and so forth. So let me acknowledge my collaborators. So Marco Biroli, who was my PhD student, he just defended this year, last year, 2025, and he's now gone to University of Chicago for postdoc. And there are many other collaborators here, some of you know probably. And earlier work with Martin Evans from Edinburgh, and also ongoing work with Urna Basu. And okay, so thank you very much for your attention.
Thank you very much. Are there any questions?
Yeah.
So physically, so the quantum reset is, so if you have a particles in a...
Quantum reset? Yeah, quantum reset means, okay, so you can think of many different ways, but one way to do this, you prepare the system in initial state psi 0, and you evolve unitarily up to a random time, and then you collapse back to psi 0 again, okay, which you can do by measurement and things like that. And then you restart, and then that drives the system into a non-equilibrium stationary state again. So, yeah.
How important is it in these computations that there's like just 2 states, or maybe just a finite number of states that you're switching between?
Right.
Like, it would make sense to me that maybe you would have like the potential is continuously change.
Yes.
In some sense.
True. No, that's true. I mean, it's just much more easier to compute this way.
Yeah.
I mean, but I think this feature of this, strong dynamical emergent correlation will be there even when it is, but it has to be stochastic. If you are, for example, doing periodically, you won't get correlation. Yeah. Yeah, exactly. So you have to have anything fluctuating that will introduce correlations between these particles. Okay. So, but it's very hard. I mean, it will be interesting to solve, a case where, this is changing by some process, which is a little bit, one problem you can do that, as I mentioned, this, where we did, so this first case where you take, instead of fluctuating the stiffness, you just take the center and you stochastically modulate. You take a one standard limit process, but you take the center, and center you're doing continuous, process something, and then you can show that indeed it again goes into a stationary state with these correlations.
Just on this point about doing it periodically
Yeah.
and not stochastically. So here, throughout the whole thing, we're assuming it's stochastic and we never know, right? Because if we have that data, then there is no correlation.
Yes.
So if you do it periodically, and you know it's periodic, but you don't know the period, then you still get correlation.
Yes, I mean, because effectively that period gets random because you don't know the yeah. But I mean, first of all, in the case of periodic thing, I mean, you would not get a strictly non-equilibrium stationary state. You will get a periodic stationary state because it will repeat, of course. Okay, and if you don't know the period, then there's a bit of an uncertainty. I mean, but if you know the period, then at a given time t, they are always uncorrelated because you just know exactly where the period is. So.
Any other question?
Yeah.
When I think of conditional IID, I think also of like Definetti's theorem and exchangeability. Is there any?
Not that I know of. Actually, I talked to many mathematicians. I mean, apparently not, there is some results by Diaconis, but not really for finite n. I don't know of any result. I mean, so this is, for me, it was a very natural question, right? If I give you a joint distribution, how do you know whether it has a CID structure or not? Okay. And this, I don't know, what is the necessary and sufficient condition for that? Yeah. Yeah. Sorry, speak. Yeah.
How they did estimate number of n? I mean,
Number of particles?
yes.
Because they do because I mean, so in the model I was putting n non-interacting particles in a single trap, okay, and then modulating this trap, right? Now in the experiment, it turns out that if you try to put many particles in a single trap, it screws up the system because there are all kinds of things, they pile up on each other. I mean, experimentally it's very hard. So what they came up with is the clever idea of putting one particle in each trap, but you synchronize the traps, you do them in the same way basically. And there you know exactly the number of particles because the number of particles is exactly the same as the number of traps. They create 4 traps and they just do this experiment.